At the very edge of our solar system drifts a deep blue world where the fastest winds ever measured roar through an endless frozen sky. Welcome to Neptune, the last giant before the darkness of interstellar space. Close your eyes and imagine sunlight so faint and so distant that midday on this world looks like twilight on Earth. From here, our sun is little more than a brilliant star, its warmth reduced to almost nothing after a journey of over 4.5 billion kilometers. And yet, despite this cold and distant exile, Neptune is anything but still. Beneath its serene blue haze churns one of the most violent atmospheres in the entire solar system, a place of ceaseless motion, hidden energy, and secrets that have taken humanity centuries to even begin to understand. For most of human history, Neptune simply did not exist, not because it wasn't there, but because no one knew to look for it. 5 planets have been visible to the naked eye since ancient times: Mercury, Venus, Mars, Jupiter, and Saturn. Generations of astronomers, philosophers, and stargazers charted the heavens without ever suspecting that 2 more worlds waited quietly in the darkness beyond. Uranus was the first to reveal itself, discovered by chance in 1781. Neptune's discovery would prove to be a very different story, not an accident, but a triumph of mathematics. By the early 19th century, astronomers had noticed something peculiar. Uranus was not moving quite the way it should. Its orbit seemed to wobble, tugged ever so slightly out of place, as though some unseen hand were pulling on it from the darkness beyond. Rather than dismiss this as an error, a handful of scientists proposed something remarkable: that an unseen planet, hidden far beyond Uranus, might be responsible for this gravitational disturbance. Working independently, the French mathematician Urbain Le Verrier and the English astronomer John Couch Adams each performed the extraordinary task of calculating where such a planet must be, using only the mathematics of gravity and the observed irregularities in Uranus's path. Neither had yet seen the planet they were describing. They had only numbers, equations, and quiet confidence in the laws that govern the movement of worlds. In September of 1846, astronomer Johann Galle at the Berlin Observatory pointed his telescope to the exact coordinates Le Verrier had calculated. Within hours he found it, a faint blue point of light, almost precisely where the mathematics had predicted. Neptune had been discovered not by chance, but by reason alone, becoming the first planet in history to be found through prediction rather than observation. There is something quietly beautiful about that moment. Long before any camera captured its swirling clouds, before any spacecraft crossed the vast gulf of space to reach it, Neptune had already been found in the mind of a mathematician, in the patient logic of orbital motion, in the simple, unshakable truth that gravity does not lie. It is a reminder that the universe often reveals itself not through what we can immediately see, but through what we are willing to carefully calculate and imagine. For a long time afterward, Neptune remained little more than that same faint point of light, a distant blue dot even through the most powerful telescopes of the era. Its extraordinary distance from Earth, some 4.5 billion kilometers at its average separation from the Sun, meant that even basic details were difficult to determine. Early astronomers could tell it was blue, could estimate its size, and could track its slow 30-year orbit around the Sun. But the storms, the winds, the moons, the rings, all of that lay hidden, waiting for technology to catch up with curiosity. Neptune holds a unique position in our solar system. It is the 8th and final planet from the Sun, the outermost of the true planets, standing sentinel at the threshold where our familiar solar neighborhood gives way to the icy, scattered debris of the Kuiper Belt and the vast emptiness beyond. Beyond Neptune, there are no more planets, only dwarf worlds like Pluto, drifting comets, and eventually, the true silence of interstellar space. In this sense, Neptune is not simply another planet. It is a boundary, a final outpost, the last blue light before the dark. Despite this significance, Neptune remains one of the least explored worlds in our solar system. Only a single spacecraft has ever traveled close enough to study it in detail, and that encounter lasted mere hours during a flyby decades ago. Everything we know about Neptune's astonishing winds, its mysterious dark storms, its faint rings, and its strange moon Triton comes largely from that single brief visit, supplemented by patient observations from telescopes here on Earth and in orbit above it. In many ways, Neptune remains a world of shadows and inference, its full nature still waiting to be uncovered by future generations of explorers. And yet, what we have learned so far is enough to captivate the imagination. A world where wind speeds surpass anything found on Earth. A planet whose interior may rain diamonds into a superheated ocean below. A moon that orbits backward, defying the usual order of things and may hide a hidden sea of its own. Neptune is not simply distant and cold. It is dynamic, mysterious, and alive with forces we are only beginning to comprehend. But Neptune's story actually began billions of years before anyone knew it existed. To understand Neptune, we must travel back, far beyond the reach of any telescope, beyond even the memory of light itself, to a time when the solar system was little more than a swirling cloud of dust and gas, spinning slowly in the darkness around a newborn star. 4.5 billion years ago, our sun did not yet shine as it does today. It was a young, gathering mass at the center of a vast disk of material, hydrogen, helium, ice, and fine grains of dust left over from the death of older stars. This disk, called the protoplanetary disk, stretched far out into space, cold and quiet, waiting for gravity to begin its slow, patient work. Somewhere within that swirling expanse, in the frigid outer reaches where sunlight barely reached, the seeds of Neptune began to form. In the outer solar system, far from the sun's gathering warmth, temperatures dropped low enough for more than just rock and metal to solidify. Water, ammonia, and methane, substances that would remain gas closer to the sun, froze into solid ice. This icy material, mixed with rock and dust, began to clump together. Tiny grains collided and stuck. Pebbles became boulders. Boulders became planetesimals, small worlds only kilometers across. And slowly, through countless gentle collisions across millions of years, these planetesimals built themselves into something larger, a growing core, layer by layer, patiently gathering mass in the cold and the dark. Once a core grew large enough, something remarkable happened. Its gravity became strong enough to begin pulling in the surrounding hydrogen and helium gas still drifting through the disk. Unlike Jupiter and Saturn, which formed closer to the sun and grew massive enough to capture enormous atmospheres of gas, Neptune's formation took place farther out, where material was scarcer and the process slower. This is why Neptune, along with its twin Uranus, became something scientists call an ice giant rather than a true gas giant, a world with a substantial icy and rocky interior, wrapped in a comparatively modest envelope of hydrogen and helium. It is a distinction that shapes everything about Neptune's character, from its internal heat to the chemistry of its brilliant blue clouds. But here is where Neptune's story takes an unexpected turn, one that scientists only began to understand in recent decades. For a long time, astronomers assumed that planets simply formed where we find them today, settling quietly into their orbits and remaining there ever since. Neptune's own history suggests something far more dramatic. The early solar system was not the calm, orderly place we observe today. It was a chaotic, crowded environment, filled with leftover debris, drifting ice, and enormous gravitational forces still settling into balance. The four giant planets, Jupiter, Saturn, Uranus, and Neptune, likely did not form in their current positions at all. Instead, growing evidence suggests they formed much closer together, packed into a tighter arrangement nearer the sun, before undergoing a slow and dramatic migration outward across hundreds of millions of years. This idea is captured in what scientists call the Nice model, named after the city in France where the theory was developed. According to this model, the gravitational interactions between the giant planets and the countless icy planetesimals surrounding them gradually shifted their orbits. As Jupiter and Saturn interacted with this surrounding disk of debris, they slowly migrated inward and outward in a delicate gravitational dance, while Uranus and Neptune were pushed steadily outward, away from the sun, toward the cold, distant realm they occupy today. In some versions of this model, the positions of Uranus and Neptune may have even switched entirely, with Neptune originally forming closer to the sun than Uranus, only to be flung outward past its neighbor during this turbulent period of gravitational rearrangement. It is a strange thought. The outermost planet in our solar system may not have started as the outermost at all. Its current position, so far from the sun's warmth, may be the result of a violent and complex gravitational history rather than a simple, quiet formation in place. This migration was not gentle. As Neptune moved outward, its gravity scattered countless small icy bodies in its path, flinging some inward toward the inner solar system and hurling others outward into the distant darkness. Many scientists believe this process is directly responsible for populating the Kuiper Belt, the vast ring of icy debris that lies beyond Neptune's orbit today. In a sense, Neptune's migration did not simply move a planet. It reshaped the entire architecture of the outer solar system, scattering material that still drifts through the darkness billions of years later. This turbulent history may also explain some of the strange characteristics we observe in Neptune today. Its moon Triton, unlike any other large moon in the solar system, orbits in the opposite direction to Neptune's own rotation, a phenomenon scientists believe resulted from Triton being a captured object rather than one that formed alongside Neptune naturally. The gravitational chaos of this early migration period offers one possible explanation for how such a capture might have occurred, as Neptune's shifting orbit and powerful gravity interacted with objects never originally meant to become its companions. It is a humbling thought when you consider it slowly. The calm, silent planet we observe today, drifting peacefully through its 30-year orbit around the Sun, carries within its very position the memory of ancient violence, of gravitational tug-of-wars between giant worlds, of scattered ice and rock flung across billions of kilometers, of a solar system still finding its balance in the early chaos of creation. Neptune's serenity today is not the absence of history, but the quiet aftermath of it. By the time this great migration settled, roughly 4 billion years ago, the solar system had largely taken the shape we recognize now. The planets had found their orbits. The debris had scattered into belts and clouds of icy bodies. And Neptune, having journeyed outward through the turbulence of its youth, settled into its distant post at the edge of the solar system. A cold, blue sentinel formed not in isolation, but through violence, motion, and the immense gravitational forces that shaped everything around it. What emerged from that chaos became one of the strangest worlds ever discovered. Imagine for a moment that you could descend into Neptune, not simply fly past it, but sink slowly through its atmosphere deeper and deeper, leaving the pale sunlight behind. What would you find? The name ice giant suggests something crystalline, something familiar, like descending into a vast frozen ocean. But the reality beneath Neptune's clouds is stranger, hotter, and far more violent than that gentle name implies. To understand Neptune, we first have to let go of what the word ice usually means to us. On Earth, ice is simply frozen water, solid, cold, and familiar. But in planetary science, the word means something broader. It refers to a category of compounds that includes water, but also ammonia and methane, chemicals that can exist as solid, liquid, or gas depending on temperature and pressure. When astronomers call Neptune an ice giant, they are not describing a planet covered in snow. They are describing its chemical recipe, a world built predominantly from these icy compounds, wrapped around a rocky core and topped with a comparatively thin layer of hydrogen and helium gas. At the very outer edge of Neptune, where sunlight last touches the planet before vanishing into its depths, lies the atmosphere we can actually observe from Earth and from passing spacecraft. This outer layer is composed primarily of hydrogen, making up the vast majority of the gas, followed by helium, much like the atmospheres of Jupiter and Saturn. But mixed within this hydrogen and helium is a small but crucial ingredient, methane. It is this methane that gives Neptune its extraordinary deep blue color. Methane absorbs red light and reflects blue light back into space, and on Neptune, this effect is even more pronounced than on Uranus, producing that unmistakable vivid sapphire hue that has captivated astronomers since Voyager's images first revealed it in striking detail. Scientists still debate why Neptune's blue appears so much richer than Uranus's paler shade, suspecting that an additional, still unidentified atmospheric component may play a role in deepening that color further. This outer atmosphere, though beautiful, is only the thinnest possible veil over what lies beneath. As you descend further into Neptune, the atmosphere does not simply end and give way to a solid surface, the way it does on Earth. There is no ground to stand on here, no clear boundary between sky and world. Instead, the atmosphere gradually thickens, the pressure climbs, and the temperature rises, until gas smoothly transitions into something far denser, a vast, swirling layer that scientists call the mantle. This mantle makes up the bulk of Neptune's mass, and it is here that the true nature of the ice giant reveals itself. Despite the icy name, temperatures within this layer soar to several thousand degrees, driven by the immense pressure of the material above pressing relentlessly downward. Under these extreme conditions, water, ammonia, and methane do not behave like the substances we know on Earth's surface. They exist instead in strange, exotic states of matter, dense, hot, electrically conductive fluids that scientists sometimes describe as a superheated slushy ocean, though even that description only hints at the bizarre physics taking place. This is not liquid water as we understand it. It is water under such extraordinary pressure and heat that it behaves almost like a molten, ionized fluid, capable of conducting electricity and generating powerful magnetic fields. This mantle layer is believed to be responsible for one of Neptune's most puzzling features, its unusual magnetic field. Unlike Earth's magnetic field, which is relatively simple and aligned closely with our planet's rotational axis, Neptune's magnetic field is dramatically tilted, offset by nearly 47 degrees from its axis of rotation, and does not even originate from the planet's center. Scientists believe this strange configuration arises directly from the swirling, electrically conductive fluids within this icy mantle, churning and generating magnetism not from a small central core, but from a much larger, more diffuse region within the planet's interior. It is a magnetic field unlike anything found on Earth, Jupiter, or Saturn, asymmetric, tilted, and deeply strange, much like the planet that produces it. Continuing deeper still, beneath this vast icy mantle, Neptune is believed to harbor a solid core, likely composed of rock and metal, similar in composition to the rocky planets of the inner solar system, though far smaller in comparison to the planet's enormous overall size. This core is thought to be roughly the mass of Earth, buried beneath thousands of kilometers of dense, superheated material above it. The pressures at this depth are almost impossible to comprehend, reaching millions of times the atmospheric pressure we experience on Earth's surface. Temperatures here may exceed those found on the surface of the sun's outer layers, a striking thought for a planet that appears, from a distance, as nothing more than a calm, cold blue orb drifting through the darkness. This layered structure, a thin outer atmosphere, a vast and exotic icy mantle, and a dense rocky core, is what defines Neptune, along with its close cousin Uranus, as fundamentally different from gas giants like Jupiter and Saturn. Jupiter and Saturn are composed overwhelmingly of hydrogen and helium, with only a comparatively small rocky and icy core buried deep within their enormous gaseous bulk. Neptune inverts this ratio almost entirely. Here, the icy and rocky material dominates, while hydrogen and helium form only a relatively thin outer shell. This is why scientists draw such a firm distinction between gas giants and ice giants, even though both categories of planets may appear, at first glance, as simply large balls of gas. What makes this internal structure so remarkable is how little of it we can actually observe directly. Everything below Neptune's visible cloud tops remains hidden from us, inferred not through direct observation, but through careful mathematical modeling, gravitational measurements, and comparisons with laboratory experiments that attempt to recreate these extreme pressures here on Earth. Scientists study Neptune's gravitational field, its magnetic field, its density, and its rotation, then use these clues to construct a model of what likely lies beneath the clouds, much like a physician interpreting the results of a scan without ever directly viewing the organ itself. This hidden interior, hot and violent despite its icy name, stands in striking contrast to the smooth, tranquil blue orb we observe from a distance. It is one of the great paradoxes of Neptune. From afar, it appears calm, serene, almost meditative in its slow, silent rotation. But beneath that peaceful blue surface lies a planet in constant turmoil, crushing pressures, superheated fluids, and a magnetic field twisted into strange and asymmetric patterns by forces still not fully understood. Yet Neptune's calm appearance hides unimaginable violence. If you could stand somewhere within Neptune's upper atmosphere, an impossible thing to do, given that there is no solid ground to stand upon, the first thing you would notice is not the cold, nor the darkness, nor even the deep blue haze surrounding you. It would be the wind. A wind unlike anything ever experienced on Earth, unlike anything found anywhere else in our solar system. A wind so powerful that it defies easy comprehension, tearing across Neptune's cloud tops at speeds that would flatten anything humanity has ever built. When Voyager 2 made its historic flyby of Neptune in 1989, scientists trained their instruments on the planet's atmosphere, expecting strong winds, given what they had already observed on Jupiter and Saturn. What they measured instead left many of them stunned. Wind speeds near Neptune's equator were recorded reaching over 2,000 kilometers per hour, some of the fastest sustained winds ever documented on any planet in our solar system. To put that number into perspective, the strongest hurricanes ever recorded on Earth reach wind speeds of perhaps 300 kilometers per hour. Neptune's winds move nearly 7 times faster than the most violent storms our own planet has ever produced, sustained not for hours or days, but continuously, relentlessly, for as long as anyone has been able to observe them. This discovery presented scientists with an immediate and deeply puzzling question. Wind, at its core, is simply the movement of atmosphere driven by energy, typically heat. On Earth, our winds are ultimately powered by the sun, which warms different parts of our planet unevenly, creating pressure differences that air rushes to equalize. The same basic principle drives weather on Jupiter and Saturn, planets that, despite their distance, still receive far more solar energy than Neptune ever could. But Neptune orbits the sun at a staggering distance, receiving only a tiny fraction of the sunlight that reaches Earth, roughly 900 times less energy than our own planet absorbs. By simple logic, a planet receiving so little solar energy should have a relatively calm, sluggish atmosphere, with little to drive such extraordinary winds. And yet Neptune is not calm. It is, in fact, the windiest planet in the entire solar system, its atmosphere in a state of near-constant, furious motion despite receiving so little warmth from the distant sun. This apparent contradiction lies at the heart of one of Neptune's greatest ongoing mysteries, an unsolved puzzle that continues to challenge planetary scientists even today. The leading explanation for this paradox lies not with the sun, but within Neptune itself. Unlike Earth, Neptune appears to generate a significant amount of its own internal heat, radiating roughly 2.5 times more energy into space than it receives from the sun. This internal heat is believed to originate from several possible sources deep within the planet. The slow, gradual contraction of the planet under its own gravity, residual heat, left over from its formation billions of years ago, and possibly even friction and chemical processes occurring within that strange, superheated mantle we explored earlier. This internal furnace, rising up from deep within Neptune's interior, may provide the energy needed to drive the planet's extraordinary atmospheric motion, even in the near-total absence of significant warmth from the sun. Curiously, Neptune's neighbor and near twin, Uranus, does not display this same behavior. Uranus radiates very little excess internal heat, and its winds, while still significant, do not reach the same staggering speeds observed on Neptune. This difference remains one of the great unresolved puzzles in planetary science, given how similar the two ice giants appear to be in size, composition, and distance from the sun. Some scientists suspect the difference may trace back to the violent, unequal histories of these two worlds. Perhaps a massive ancient collision disrupted Uranus's internal heat flow in a way that never happened to Neptune, though this remains an area of active research and ongoing debate. Neptune's winds do not blow uniformly across the entire planet. Like Earth and like the other giant planets, Neptune's atmosphere is organized into distinct bands of circulation, running parallel to its equator. Near the equator itself, the winds blow in a direction opposite to the planet's own rotation, a phenomenon scientists call retrograde flow. Moving toward the poles, this pattern reverses, with winds instead blowing in the same direction as Neptune's rotation. This banded structure of alternating wind patterns, though found in modified forms on Jupiter and Saturn as well, reaches an extreme intensity on Neptune that remains unmatched anywhere else in the solar system. Within these powerful wind bands, Neptune's atmosphere also produces enormous, swirling storm systems, some large enough to rival the size of entire continents on Earth. The most famous of these, observed by Voyager 2 during its historic flyby, was a colossal dark storm named the Great Dark Spot, an enormous, oval-shaped feature bearing a striking visual resemblance to Jupiter's famous Great Red Spot, though composed of entirely different atmospheric processes and behaving in far less predictable ways. Winds along the edges of this storm system were measured at speeds nearing the fastest ever recorded anywhere on the planet, driven by the powerful energy differences between the storm and the surrounding atmosphere. What makes Neptune's storms particularly fascinating and particularly mysterious is how quickly they can change. Unlike Jupiter's Great Red Spot, a storm system that has persisted in some form for centuries, Neptune's dark storms appear far less stable, sometimes forming, growing, and then disappearing entirely within just a few years. When the Hubble Space Telescope observed Neptune years after Voyager's flyby, the Great Dark Spot that had once dominated the planet's southern hemisphere had vanished completely, replaced instead by entirely new storm systems that had formed in different locations across the planet. This dynamic, ever-shifting nature of Neptune's storms stands in stark contrast to the ancient, slow-moving weather systems observed on Jupiter, suggesting fundamentally different processes at work deep within Neptune's turbulent atmosphere. Scientists continue to study these storms closely, using powerful telescopes here on Earth and in orbit to track their formation and evolution from a distance. Each new storm offers valuable clues about the deeper atmospheric processes driving Neptune's extraordinary weather, though many fundamental questions remain unanswered. Why do Neptune's storms form and dissipate so quickly compared to Jupiter's? What triggers their sudden appearance in seemingly random locations across the planet? And how exactly does the planet's internal heat translate into such extraordinarily fast, sustained winds at the cloud tops, so far removed from the deep interior where that heat originates? These are the kinds of questions that keep Neptune firmly in the minds of planetary scientists, even decades after our only close visit. Every fresh observation, whether from Hubble, from ground-based telescopes, or from future missions yet to be planned, adds another small piece to an atmospheric puzzle that remains, in many ways, as mysterious today as it was when Voyager 2 first measured those astonishing wind speeds back in 1989. But where do these powerful storms come from? To truly understand Neptune's storms, we have to move beyond the winds that drive them and look instead at the storms themselves. Vast, shifting structures that rise and fall across the planet's surface like slow, silent breaths, each one a brief and turbulent chapter in an atmosphere that never seems to rest. When Voyager 2's cameras first captured the Great Dark Spot in 1989, scientists were looking at something they did not fully expect to find. This immense storm system, roughly the size of Earth itself, appeared as a dark, oval blemish set against Neptune's brilliant blue backdrop, rotating counterclockwise and drifting slowly across the southern hemisphere. Unlike Jupiter's Great Red Spot, which owes its ruddy color to complex chemical compounds churned up from deep within the planet, the darkness of Neptune's storm seemed to result from something different entirely, a gap or clearing in the upper cloud deck, allowing observers to peer slightly deeper into the atmosphere below, into a region that simply appeared darker by comparison to the bright clouds surrounding it. What made this storm particularly captivating were the clouds that accompanied it. Hovering near the edges of the Great Dark Spot, Voyager's instruments detected brilliant white, wispy formations that scientists nicknamed the scooter clouds, a playful name for features that moved rapidly around the planet, completing full circuits faster than the dark storm they seemed to trail alongside. These white clouds are composed primarily of methane ice crystals, condensing out of the atmosphere, much like water vapor forms clouds here on Earth, though at temperatures and altitudes almost impossible to imagine from the surface of our own world. Bright, high altitude, and constantly shifting, these methane clouds cast faint shadows onto the deeper cloud layers below, giving scientists one of their only visual tools for measuring the actual altitude and structure of Neptune's atmosphere from such a vast distance. Perhaps the most surprising discovery about Neptune's storms came years later, not from a spacecraft, but from the Hubble Space Telescope, patiently observing the planet from Earth orbit. When Hubble turned its attention to Neptune in the mid-1990s, astronomers searched for the great dark spot that had so captivated the world just a few years earlier. It was simply gone. In its place, an entirely new dark storm had formed in the northern hemisphere, appearing seemingly out of nowhere, following no discernible pattern tied to the storm that had vanished before it. This behavior stands in remarkable contrast to Jupiter's Great Red Spot, a storm system that has persisted, by some estimates, for well over 300 years, tracked continuously by astronomers since the invention of the telescope. Jupiter's storm rotates steadily within a well-defined band, drawing energy from the planet's massive internal heat and enormous atmospheric reservoirs in a way that allows it to sustain itself across centuries, with only gradual changes in size and intensity. Neptune's storms behave nothing like this. They appear abruptly, sometimes growing rapidly over the course of just a few months, only to weaken, drift toward the equator, and dissolve entirely within a handful of years. Scientists studying these differences believe Neptune's smaller size relative to Jupiter, combined with its unique internal heat dynamics and thinner atmospheric envelope, may prevent its storms from achieving the same long-term stability, though the full explanation remains an active area of research. This impermanence gives Neptune's atmosphere a strange, almost restless character. Where Jupiter's clouds feel ancient, settled into patterns that have existed for longer than most human institutions, Neptune's clouds feel transient, caught in a state of constant reorganization. Giant vortices form and dissolve. Bright cloud bands appear, brighten, and fade. Storm systems race across the planet's face and vanish before any two observations can fully capture their entire life cycle. It is a planet that seems, in its own quiet way, to be perpetually rewriting itself. Adding another layer of complexity to this restless weather is Neptune's remarkably long orbit around the Sun, taking approximately 165 Earth years to complete a single circuit. Because of this immense orbital period, each of Neptune's seasons stretches across roughly 4 decades of Earth time, a length of time that makes tracking seasonal atmospheric change an extraordinarily slow and patient endeavor for scientists studying the planet from afar. Some researchers believe Neptune's brightness and storm activity may shift gradually according to these long seasonal cycles, tied to the subtle changes in sunlight reaching different latitudes of the planet as it slowly progresses along its multi-decade orbital journey. Ground-based observations spanning several decades have hinted at such seasonal brightening and dimming, though confirming these patterns requires the kind of sustained, long-term study that few scientific careers are long enough to complete alone. Neptune's cloud dynamics also reveal fascinating details about the layered structure of its atmosphere. The bright, high-altitude methane clouds we can observe from Earth and from passing spacecraft sit atop deeper, less visible cloud layers believed to be composed of other compounds, including hydrogen sulfide and ammonia-based ices, layers that remain largely hidden beneath the more prominent methane haze above. These deeper clouds occasionally become visible through gaps and clearings in the upper atmosphere, offering scientists rare and valuable glimpses into the planet's internal weather structure. Much like brief openings in a thick fog, allow a distant observer to glimpse the landscape hidden beneath. Taken together, these storms, clouds, and shifting atmospheric bands paint a picture of a planet locked in constant transformation, its surface a canvas that never holds the same image for very long. And yet, for all this visible turbulence and change, the true source of Neptune's restless energy lies not within the clouds themselves, but far below them, in a hidden interior world of crushing pressure and extraordinary heat. Deep beneath those clouds lies an even stranger interior. Beneath Neptune's restless clouds, past the layer of superheated fluid we call the mantle, lies a realm so extreme that it challenges the very language we use to describe matter. Here, deep within the planet, pressure and temperature combine in ways that transform familiar substances into something almost unrecognizable, and give rise to one of the strangest phenomena ever proposed in planetary science. To appreciate just how extreme conditions become inside Neptune, it helps to first understand the scale of pressure involved. At Earth's surface, we experience one atmosphere of pressure, a value so constant and familiar that we rarely think about it at all. Descend into Neptune's interior, however, and that pressure climbs at an almost unimaginable rate. By the time you reach the boundary between the mantle and the core, pressures may exceed several million times what we experience on Earth's surface. Under this kind of crushing force, ordinary rules of chemistry begin to bend. Within this high-pressure environment, scientists believe that methane, the very same compound responsible for Neptune's brilliant blue color in the upper atmosphere, undergoes an extraordinary transformation deep within the planet's mantle. Methane is a molecule built from carbon and hydrogen atoms. Under normal conditions, these atoms remain bonded together in a stable, predictable structure. But under the immense pressures and temperatures found deep inside Neptune, some scientists theorize that these methane molecules may be forced apart, breaking their bonds and releasing pure carbon in the process. And what does pure carbon become under sufficiently extreme pressure? Diamond. This idea, often referred to as the diamond rain hypothesis, suggests that deep within Neptune's mantle, tiny crystals of solid carbon may form, and then, being denser than the surrounding fluid, begin to sink slowly downward through the planet's interior, much like raindrops falling through Earth's atmosphere, except these raindrops are falling through superheated, high-pressure fluid rather than air, and they are made of diamond rather than water. Over time, these sinking diamond fragments may grow larger as they descend, eventually accumulating near the boundary of Neptune's rocky core, potentially forming a layer of solid or semi-solid diamond material, unlike anything found naturally on Earth's surface. For decades, this idea remained purely theoretical, a fascinating but unproven hypothesis based on our understanding of chemistry and physics under extreme conditions. But in recent years, scientists have taken remarkable steps to actually test this theory here on Earth, using laboratory techniques capable of recreating, at least briefly, the kind of pressures and temperatures found deep within ice giants like Neptune. In these experiments, researchers use powerful lasers to compress small samples of material similar in composition to Neptune's interior, generating shockwaves that briefly recreate pressures and temperatures resembling those found thousands of kilometers beneath Neptune's clouds. During some of these experiments, scientists have indeed observed the formation of small diamond structures, offering compelling, though still indirect, evidence that the diamond rain hypothesis may accurately describe real processes occurring within Neptune's interior at this very moment. It remains one of the more remarkable examples in modern science of researchers reaching across billions of kilometers, using nothing more than lasers and careful measurement, to test a theory about the interior of a planet none of us will ever visit directly. If this hypothesis holds true, it paints an almost dreamlike picture of Neptune's hidden depths, a vast, dark ocean of superheated, electrically conductive fluid, illuminated only by the faint, ongoing formation of diamonds slowly drifting downward through the crushing pressure. Accumulating perhaps into a solid layer surrounding the planet's rocky core, a treasure beyond imagination, forever hidden beneath thousands of kilometers of dense material, utterly inaccessible to any spacecraft or instrument humanity could ever hope to send there. This exotic interior chemistry also offers scientists valuable insight into the broader behavior of matter under extreme conditions, insight that extends well beyond Neptune itself. Understanding how methane, water, and ammonia behave under these crushing pressures helps researchers model the interiors of other ice giants throughout the galaxy, including the countless similarly sized exoplanets discovered orbiting distant stars. In many ways, Neptune serves as a natural laboratory, a nearby example of ice giant physics that helps scientists interpret worlds far too distant to study in any direct detail. The temperatures involved in this deep interior process are similarly staggering. Some models suggest that near Neptune's core, temperatures may reach several thousand degrees Celsius, hot enough to rival, and in some estimates even exceed, the temperature found at the surface of the Sun. And yet, despite this incredible internal heat, Neptune's outer atmosphere remains bitterly cold, its cloud tops hovering at temperatures far below anything experienced anywhere on Earth. This extraordinary contrast between a frozen outer face and a superheated interior captures something essential about Neptune's nature. It is a planet of extremes, layered with contradictions, calm and frozen on the surface, yet fierce and transformative in its hidden depths. If Neptune's inside seems unbelievable, its moons are just as extraordinary. Of all the strange and wonderful objects that orbit Neptune, none captures the imagination quite like Triton, a moon so unusual, so seemingly out of place, that its very existence forces us to reconsider what we thought we understood about how moons are supposed to form. At first glance, Triton might seem unremarkable among the many moons scattered throughout our solar system. It is large, roughly 2,700 kilometers across, making it the seventh largest moon in the entire solar system, and easily the largest of Neptune's 14 known moons. But its size is not what makes Triton so extraordinary. It is the way it moves. Nearly every large moon in our solar system orbits its parent planet in the same direction that the planet itself rotates, a natural consequence of forming together from the same swirling disk of material billions of years ago. Triton breaks this pattern entirely. It orbits Neptune backward, moving in the opposite direction to the planet's own rotation, a phenomenon astronomers call a retrograde orbit. Among all the large moons in our solar system, Triton stands alone in exhibiting this behavior, a lonely exception to a rule that otherwise holds true almost everywhere else we look. This backward orbit is not simply a curious footnote. It is powerful evidence that Triton did not form alongside Neptune at all. Instead, scientists believe Triton originated somewhere else entirely, likely within the distant Kuiper Belt, the vast region of icy bodies extending beyond Neptune's orbit. At some point in the ancient past, Triton is thought to have wandered too close to Neptune's powerful gravity and become captured, pulled permanently into orbit around a planet it was never originally meant to circle. This idea is further supported by Triton's composition and characteristics, which closely resemble those of Pluto and other icy dwarf worlds found within the Kuiper Belt, rather than moons that formed naturally alongside their host planets. The process of this capture would have been anything but gentle. Scientists believe that as Triton was gradually pulled into a stable orbit around Neptune, gravitational forces would have significantly heated its interior through intense tidal flexing, a process similar to how gravitational interactions generate heat within other moons throughout the solar system, though likely far more extreme in Triton's case given the dramatic nature of its capture. This early period of intense heating may have partially melted Triton's interior, allowing heavier materials to sink toward its center, while lighter ices rose toward the surface, ultimately shaping the internal structure we infer exists within the moon today. When Voyager 2 passed by Neptune in 1989, it captured our only close, detailed images of Triton, revealing a world unlike almost anything else observed in the outer solar system. Rather than a uniformly cratered, ancient surface, common to many icy moons that have remained geologically inactive for billions of years, Triton displayed a surface remarkably young and varied, marked by strange, wrinkled terrain that scientists nicknamed cantaloupe terrain due to its resemblance to the textured skin of the fruit. This unusual landscape suggests ongoing or relatively recent geological activity, a surprising finding for a small, icy moon located so far from the warmth of the sun. Perhaps the most striking discovery Voyager made at Triton was the presence of active geysers, erupting directly from the moon's frozen surface. These geysers shoot dark plumes of nitrogen gas and fine dust particles several kilometers into Triton's thin atmosphere, where they are then carried sideways by high-altitude winds before slowly settling back down onto the surface, leaving long, dark streaks visible across the icy landscape. At the time, this made Triton only the third body in the solar system, after Earth and Jupiter's moon Io, known to display active geological venting of this kind, a remarkable discovery for a moon so distant and so cold. The mechanism driving these geysers remains a subject of ongoing scientific investigation, though the leading explanation involves a fascinating interaction between sunlight and Triton's icy surface. Despite Triton's extreme distance from the sun and correspondingly frigid surface temperature, Some scientists believe that sunlight penetrating through a translucent layer of surface ice may warm subsurface nitrogen ice just enough to cause it to vaporize, building up pressure beneath the surface until it eventually bursts through in these dramatic geyser eruptions, similar in some ways to how a greenhouse traps heat, only occurring beneath a thin layer of frozen nitrogen rather than glass. Triton also possesses a remarkably thin atmosphere of its own, composed primarily of nitrogen with trace amounts of methane, a delicate envelope of gas so thin that its surface pressure measures merely a tiny fraction of what we experience here on Earth. Despite its thinness, this atmosphere is significant enough to support visible clouds, hazes, and the sideways transport of material ejected from Triton's geysers, offering scientists a small but valuable window into the Moon's ongoing atmospheric and geological processes. Given its likely icy composition and evidence of past internal heating, some scientists have proposed that Triton may harbor a subsurface ocean of liquid water, hidden beneath its frozen outer crust, warmed by a combination of residual internal heat and ongoing tidal forces generated by its orbit around Neptune. If true, this would place Triton among a growing list of ocean worlds discovered throughout our solar system, alongside moons like Europa and Enceladus, expanding the range of places where the fundamental ingredients for life, as we understand them, might theoretically exist. This remains an area of significant scientific interest, and one that future missions to the Neptune system may eventually help clarify. Triton's unusual retrograde orbit carries with it one final remarkable consequence, one that unfolds not within our own lifetimes, but across an almost unimaginable span of cosmic time. Because Triton orbits in the opposite direction to Neptune's rotation, gravitational tidal forces are gradually causing its orbit to decay, pulling the Moon slowly but steadily closer to Neptune with each passing orbit. Over an estimated span of several billion years, scientists predict that Triton will eventually drift close enough to Neptune that the planet's powerful gravity will tear the Moon apart entirely, most likely forming a spectacular ring system around Neptune, one that may, for a brief cosmic moment, rival or even exceed the grandeur of the rings we see around Saturn today. It is a strange thought, sitting quietly with the idea that this Moon, captured so long ago and carried into an orbit it was never meant to occupy, is even now being drawn slowly toward its own eventual destruction, a fate written into its very trajectory from the moment it was first pulled into Neptune's gravitational embrace. Yet Triton isn't Neptune's only fascinating companion. Long before Voyager 2 ever reached Neptune, astronomers already suspected the planet might be hiding something more than just its large, unusual moon. Faint hints observed from Earth suggested the possible presence of rings, though nothing could be confirmed with certainty until a spacecraft finally arrived close enough to see for itself. What Voyager 2 revealed in 1989 was a ring system unlike any other found in our solar system, faint, fragmented, and full of mysteries that scientists are still working to fully understand. Neptune possesses a system of rings, though they bear little resemblance to the bright, broad, and easily visible rings encircling Saturn. Where Saturn's rings are composed of countless icy particles, reflecting sunlight brilliantly across a vast, well-defined structure, Neptune's rings are dark, narrow, and remarkably faint, composed largely of fine dust particles mixed with small amounts of ice, absorbing far more light than they reflect. This darkness makes them exceptionally difficult to observe from Earth, and even challenging to photograph clearly from a passing spacecraft, requiring careful specialized imaging techniques to capture their delicate structure against the darkness of space. In total, Neptune possesses 5 main rings, each named after astronomers who contributed significantly to the study and eventual confirmation of Neptune's existence and characteristics. Moving outward from the planet, these rings are named Gala, Leverrier, Lassell, Arago, and Adams, honoring figures whose calculations and observations helped bring Neptune itself out of obscurity nearly 2 centuries ago. It is a fitting tribute, embedding the history of Neptune's discovery directly into the naming of the delicate structures that encircle it. Among these rings, the outermost, named Adams, holds a particularly fascinating secret. Rather than forming a smooth, continuous band of material like most planetary rings, portions of the atom's ring are notably clumped together into distinct, brighter segments, dense concentrations of material, separated by comparatively empty stretches along the same ring path. Scientists refer to these dense clumps as ring arcs, and their existence presented a genuine puzzle when first observed. Under normal circumstances, gravitational and orbital dynamics would be expected to spread ring material evenly around a planet over time, gradually smoothing out any such uneven clumping. The fact that these arcs persist, rather than dispersing into a uniform ring, suggested that some additional gravitational influence must be holding them together. The answer, scientists believe, lies with small, nearby moons acting as gravitational shepherds. Just as certain small moons around Saturn help maintain the sharp, well-defined edges of that planet's rings through their gravitational influence, a small moon named Galatea, orbiting just inside the atom's ring, is thought to play a similar role in maintaining Neptune's ring arcs, its gravity subtly nudging nearby ring particles into these stable, clumped configurations, rather than allowing them to disperse evenly around the planet. This delicate gravitational balancing act offers a beautiful example of how even very small, faint objects can meaningfully shape the structure of much larger systems around them, a reminder that scale alone does not determine influence within the intricate mechanics of orbital motion. Beyond Triton and the rings, Neptune hosts a modest but intriguing family of smaller moons, 13 additional satellites beyond Triton itself, though most remain far less studied and considerably less understood. Some of these smaller moons orbit closer to Neptune, likely composed of icy and rocky debris remaining from the planet's ancient formation, or perhaps material disrupted during Triton's dramatic and violent capture billions of years ago. Others orbit much farther out, following distant, irregular paths that suggest they too may be captured objects, drawn in from the surrounding Kuiper belt much like Triton itself, though on a smaller and less dramatic scale. One particularly interesting example among these smaller moons is Nereid, notable for possessing one of the most eccentric, elongated orbits of any moon in the solar system. Rather than following a neat, nearly circular path around Neptune, Nereid's orbit stretches dramatically inward and outward, its distance from the planet varying enormously over the course of each orbit. This highly unusual orbital behavior further reinforces the picture scientists have gradually assembled of the Neptune system as a whole, a chaotic and dynamic environment shaped significantly by Triton's disruptive arrival, an event whose gravitational ripples appear to have influenced the orbits and characteristics of numerous smaller bodies throughout the system, effects that persist even today, billions of years later. Many of Neptune's smaller, more distant moons were only discovered decades after Voyager's flyby, identified instead through patient, careful observation using powerful ground-based telescopes and orbital observatories like Hubble, capable of detecting faint points of reflected light too small and too dim for Voyager's instruments to have captured during its brief, single pass through the system. This ongoing discovery process highlights just how much about Neptune's broader system likely remains unknown, hidden not through any fundamental mystery, but simply through the practical limitations of observing such faint, distant objects from so many billions of kilometers away. Taken together, Neptune's rings and smaller moons form a delicate, interconnected system, shaped by gravity, ancient collisions, and the singular disruptive event of Triton's capture, a system that continues to intrigue scientists precisely because so much of it remains just barely beyond the reach of our current instruments and understanding. Each new observation, each faint new moon discovered, adds another small piece to a puzzle that likely will not be fully solved without a dedicated mission returning to study Neptune directly, something that has not occurred in more than 3 decades. Only one spacecraft has ever visited this distant giant. On August 25, 1989, humanity accomplished something it would not repeat for the rest of the 20th century and has not repeated since. A spacecraft, launched 12 years earlier and already far beyond its original planned mission, swept past the outermost planet in our solar system, capturing our first, and to this day our only, close look at Neptune and its strange family of moons. Voyager 2 had already achieved remarkable things by the time it reached Neptune. Launched in 1977 alongside its twin, Voyager 1, the spacecraft had already completed historic flybys of Jupiter in 1979, Saturn in 1981, and Uranus in 1986, each encounter revealing extraordinary new details about these distant worlds and their moons. Neptune represented the final planetary encounter of this grand journey, a fitting conclusion to what remains one of the most scientifically productive missions in the history of space exploration. After Neptune, Voyager 2 would continue outward, eventually leaving the solar system entirely, but this flyby marked the last time the spacecraft would study a planet up close. The journey to Neptune alone had taken Voyager 2 12 years, traveling across a distance so vast that even light, moving at its incredible constant speed, takes over 4 hours to cross it. Communication with the spacecraft during this period involved a strange, patient rhythm. Commands sent from Earth took over 4 hours simply to reach the spacecraft, and any response or data sent back required another 4 hours to return, meaning that mission scientists on Earth were always working with information that was already hours old, and any commands they sent would not take effect until hours after they were transmitted. Coordinating a precise, close flyby of a planet under these communication delays required extraordinary planning and precision, with much of the spacecraft's flyby sequence programmed well in advance, trusting Voyager 2's own onboard systems to execute the encounter correctly without the possibility of real-time correction from mission control. Voyager 2's closest approach to Neptune brought the spacecraft within about 3,000 kilometers of the planet's cloud tops, a remarkably close pass that allowed its instruments to capture detailed images and measurements unavailable through any telescope on or near Earth. This close approach, combined with a subsequent flyby of Triton just hours later, meant that in a single brief period, Voyager 2 fundamentally transformed our understanding of both Neptune and its largest moon, revealing details that Earth-based astronomers had only been able to guess at for over a century. Among Voyager 2's most significant discoveries was direct confirmation of Neptune's extraordinarily powerful winds, with instruments measuring atmospheric speeds far exceeding anything previously observed on any planet, definitively establishing Neptune as the windiest world in our solar system. The spacecraft also captured detailed images of the Great Dark Spot, allowing scientists to study its structure, movement, and surrounding cloud patterns in a level of detail that had been utterly impossible from Earth-based observations alone. Alongside this massive storm, Voyager's cameras also identified the fast-moving white clouds nicknamed the Scooter, along with numerous smaller storm systems scattered across the planet's turbulent atmosphere. Voyager 2 also provided the first direct confirmation of Neptune's ring system, resolving the faint, uncertain hints that ground-based astronomers had puzzled over for years. The spacecraft's instruments revealed the ring's unusual clump structure, identifying what we now call ring arcs, and provided the data necessary to eventually understand the gravitational shepherding effect of the small moon Galatea in maintaining this unusual formation. Without this close encounter, the true nature of Neptune's rings would likely have remained uncertain and poorly understood for many more decades. Perhaps most significantly, Voyager 2 provided our only direct measurements of Neptune's magnetic field, revealing its dramatic and unexpected tilt of nearly 47 degrees relative to the planet's rotational axis, along with its unusual offset from the planet's actual center. This discovery fundamentally reshaped scientific understanding of how magnetic fields can form within ice giants, suggesting that Neptune's magnetism arises from a broad, dynamic region within its icy mantle, rather than a smaller, more centrally located core, a finding with significant implications for how scientists model the interiors of ice giants throughout the galaxy. At Triton, Voyager 2 delivered an equally extraordinary series of discoveries, capturing detailed images of the moon's unusual cantaloupe terrain, along with clear evidence of active geysers erupting from its icy surface, complete with visible dark streaks where ejected material had settled back down after being carried by high-altitude winds. These images provided the first direct evidence of ongoing geological activity on Triton, transforming scientific understanding of the moon from a presumed frozen, inactive world into a dynamic, geologically active body worthy of significant further study. Beyond these headline discoveries, Voyager 2's instruments gathered enormous amounts of additional data during its brief encounter, measuring Neptune's temperature, atmospheric composition, and overall structure in far greater detail than had ever been possible before, while also identifying several previously unknown smaller moons within the Neptune system, expanding the known family of satellites orbiting the distant planet. And yet, for all it revealed, Voyager 2's flyby lasted only a matter of hours, a single, brief pass through a system that likely holds far more secrets than any spacecraft moving at such tremendous speed could hope to fully capture. Many discoveries raised as many new questions as they answered. The exact mechanism driving Neptune's internal heat remains uncertain. The precise composition of the deep atmosphere remains only partially understood. The full extent of geological activity on Triton and the possibility of a hidden subsurface ocean remains an open question that only a dedicated future mission could hope to properly investigate. In the decades since Voyager 2's historic flyby, no other spacecraft has traveled to Neptune, leaving this single, brief encounter as the sole source of close-up data humanity possesses about this distant, mysterious world. Everything learned since then has come instead from careful, patient observation, using powerful telescopes here on Earth and in orbit above it, valuable but inherently limited compared to the detailed measurements only a close flyby, or ideally an orbiting spacecraft, could ultimately provide. More than 3 decades later, many of Neptune's biggest mysteries remain unsolved. For all that Voyager 2 revealed during its brief encounter, and for all that patient observation from Earth has added in the decades since, Neptune remains, in many fundamental ways, a planet defined as much by its open questions as by its confirmed discoveries. Scattered throughout everything we have learned about this distant world are gaps, contradictions, and unresolved puzzles that continue to occupy the attention of planetary scientists even today. Perhaps the most persistent of these mysteries concerns Neptune's internal heat. We know with reasonable confidence that Neptune radiates significantly more energy into space than it receives from the Sun, a clear signal that something deep within the planet continues to generate substantial heat billions of years after its formation. But the precise source of this heat remains genuinely uncertain. Some scientists point to slow, ongoing gravitational contraction, the planet very gradually shrinking under its own weight and converting that gravitational energy into heat. Others suggest that chemical processes within the icy mantle, including the very formation of diamonds theorized to rain slowly toward the core, might release additional thermal energy as a byproduct. Still others wonder whether residual heat from Neptune's violent formation and migration billions of years ago might simply be escaping more slowly than expected, trapped by layers of material that resist releasing it quickly. Without a mission capable of directly probing Neptune's deep interior, distinguishing between these competing explanations remains extremely difficult, leaving this fundamental question about the planet's basic energy budget unresolved. Closely tied to this mystery is an even stranger puzzle involving Neptune's close cousin, Uranus. Despite being remarkably similar in size, composition, and distance from the Sun, Uranus does not display anywhere near the same level of internal heat that Neptune does, nor does it experience wind speeds approaching Neptune's extraordinary velocities. Two planets born under broadly similar conditions in the early solar system have somehow ended up with dramatically different internal energy budgets, and by extension, dramatically different atmospheric behavior. Some scientists suspect this difference may trace back to a massive ancient impact, one theorized to have struck Uranus early in its history, potentially disrupting its internal heat flow in ways that never affected Neptune. But this remains speculative, a hypothesis awaiting further evidence rather than a confirmed explanation, leaving the stark contrast between these two otherwise similar worlds as one of the more compelling unsolved comparisons in planetary science. Neptune's magnetic field presents its own set of unresolved questions. We know, thanks to Voyager 2's measurements, that this magnetic field is unusually tilted and significantly offset from the planet's center. Behavior scientists attribute to the churning, electrically conductive fluids believed to exist within Neptune's icy mantle. But the precise details of exactly how this magnetic field is generated, how stable it remains over long periods of time, and how it interacts with the solar wind and Neptune's moons, particularly Triton, remain only partially understood, based on a single brief measurement taken more than 3 decades ago, rather than the kind of sustained, continuous observation that would be needed to fully characterize its behavior over time. The precise chemical composition of Neptune's deep atmosphere also remains something of an open question. While scientists have confidently identified hydrogen, helium, and methane within the planet's outer layers, the exact abundance and distribution of other compounds, including water, ammonia, and hydrogen sulfide, particularly within the deeper, less visible layers of the atmosphere, remains based largely on theoretical modeling rather than direct measurement. Determining these deeper atmospheric details would require an instrument capable of descending into the atmosphere itself, similar to the probe that Jupiter's Galileo mission famously released years ago, an approach that has never yet been attempted at Neptune. Neptune's ever-changing storm systems present their own ongoing puzzle as well. Scientists still do not fully understand exactly what triggers the sudden formation of dark storms like the Great Dark Spot Voyager observed, nor precisely why these storms behave so differently from the far more persistent storm systems found on Jupiter. Continued monitoring using telescopes like Hubble has revealed that new dark storms periodically appear and disappear across Neptune's surface, but predicting exactly when and where the next such storm might form remains beyond current scientific capability, limited by the relatively sparse, infrequent observations available for such a distant planet. Even something as seemingly basic as Neptune's precise rotation rate has proven surprisingly difficult to pin down with complete confidence. Because Neptune lacks any solid surface features that could be tracked consistently over time, scientists must instead rely on measurements of its magnetic field and radio emissions to estimate how quickly the planet's deep interior rotates, a method that has produced measurements evolving somewhat over the decades as instruments and analysis techniques have improved. This ongoing refinement highlights just how many basic physical properties of Neptune remain less precisely known than one might initially assume for a major planet within our own solar system. Taken together, these unresolved questions paint a picture of a planet that, despite centuries of study and one historic close encounter, remains only partially understood. Neptune sits at a challenging intersection within planetary science, too distant and too difficult to reach for frequent study, yet too scientifically important, particularly given how common ice giants appear to be throughout the broader galaxy, to simply set aside as a solved problem. Every new observation, whether from ground-based telescopes, orbiting observatories, or future dedicated missions, offers the possibility of resolving one small piece of this larger puzzle, gradually bringing this distant, windswept world into clearer focus. Could humans ever travel this far? To grasp what it would truly mean to send humans to Neptune, we first have to sit with the sheer scale of the distance involved, a distance so vast that it strains ordinary intuition, built as it is on the more modest scales of travel we experience in everyday life here on Earth. Neptune orbits the Sun at an average distance of roughly 4.5 billion kilometers, a figure so large that expressing it in kilometers alone barely helps us comprehend it. Astronomers often use a different unit for such distances, the astronomical unit, defined as the average distance between Earth and the Sun. By this measure, Neptune sits at approximately 30 astronomical units from the Sun, meaning it is roughly 30 times farther from the Sun than Earth itself. Light, traveling at its famously fast and constant speed, takes over 4 hours to cross this distance, meaning that any signal sent from Earth to a spacecraft near Neptune arrives only after a journey longer than most people's entire workday. Voyager 2, moving at tremendous speed relative to anything humans have built for everyday travel, still required 12 full years to reach Neptune after its 1977 launch, and that was without any attempt to slow down or enter orbit around the planet, simply a fast, direct flyby. For context, this means a round-trip conversation with a spacecraft near Neptune, a single question sent, and a single answer received, takes over 8 hours to complete, even at the speed of light. Any human mission attempting to travel to Neptune would face this same fundamental challenge, magnified considerably by the additional requirements of keeping a human crew alive, healthy, and psychologically stable across a journey lasting well over a decade using current propulsion technology. The challenges facing any theoretical human mission to Neptune extend far beyond simply enduring a long journey. Spacecraft traveling to the outer solar system must contend with steadily decreasing sunlight, a serious challenge given that most spacecraft rely on solar panels to generate electrical power. By the time a spacecraft reaches Neptune's distance from the Sun, sunlight has weakened to roughly 900 times less intense than what we experience on Earth, far too faint to reliably power spacecraft systems using conventional solar panels alone. This is why Voyager 2, along with most missions traveling to the outer solar system, relies instead on radioisotope thermoelectric generators, devices that generate electricity from the slow, steady heat released by the natural decay of radioactive material, a power source capable of functioning reliably regardless of how far a spacecraft travels from the sun's diminishing light. Radiation exposure presents another serious obstacle for any human crew attempting such a distant journey. Without the protective shielding provided by Earth's magnetic field and thick atmosphere, astronauts traveling through deep space for over a decade would face significantly elevated exposure to cosmic radiation, a level of exposure that current spacecraft shielding technology struggles to adequately address for missions of this extraordinary duration. Solving this challenge would likely require significant advances in materials science, shielding design, or propulsion technology capable of dramatically shortening travel time, none of which currently exist in a form ready for practical implementation. Even setting aside the question of transportation entirely, the idea of actually landing on Neptune presents an insurmountable challenge, simply because Neptune has no solid surface to land upon at all. As we explored earlier, Neptune's atmosphere gradually thickens with depth, transitioning smoothly into an exotic, superheated fluid mantle, without ever passing through anything resembling a solid, walkable surface. Any spacecraft, human-crewed or otherwise, attempting to descend into Neptune's atmosphere would eventually encounter crushing pressures and extreme temperatures long before reaching anything that could be considered solid ground, making traditional landing entirely impossible by definition. Given these overwhelming challenges, scientists studying the possibility of future Neptune exploration have focused almost entirely on robotic missions rather than any form of human spaceflight, at least for the foreseeable future. Several concepts for future robotic missions to Neptune have been proposed over the years, including dedicated orbiter missions designed to study the planet continuously over an extended period, rather than the brief, single flyby Voyager 2 provided decades ago. Such a mission could finally offer sustained measurements of Neptune's magnetic field, detailed mapping of its ever-changing storm systems, and continuous monitoring of Triton's geological activity, addressing many of the open questions that a single historic flyby simply could not resolve. Some proposed missions have also included the concept of an atmospheric probe, a small instrument package designed to be released from a larger orbiting spacecraft and sent descending directly into Neptune's atmosphere, similar in concept to the probe that plunged into Jupiter's atmosphere during the Galileo mission years ago. Such a probe, even surviving only a brief period before succumbing to the extreme pressures and temperatures of Neptune's deeper atmosphere, could provide invaluable direct measurements of atmospheric composition and structure, data currently available only through indirect observation and theoretical modeling from a great distance. Despite growing scientific interest in returning to Neptune, no dedicated mission has yet been fully approved and funded for launch, largely due to the enormous cost, extended mission duration, and significant technical challenges involved in reaching such a distant world. Some proposals suggest that even with current propulsion technology, a dedicated orbiter mission could take well over a decade simply to reach Neptune, followed by additional years of operation once it arrives, representing an enormous, multi-decade commitment of resources and scientific attention for any space agency considering such an ambitious undertaking. For now then, Neptune remains a world studied from a distance, understood through the brief historic glimpse Voyager 2 provided decades ago, supplemented by patient, ongoing observation from telescopes here on Earth and in orbit above it. Perhaps within the coming decades, renewed scientific interest and advancing technology will finally justify sending a new spacecraft back to this distant, windswept world, continuing a journey of exploration that began not with a spacecraft at all, but with careful mathematics and a small, patient telescope pointed at exactly the right point in the night sky, nearly 2 centuries ago. One day, even Neptune will face an inevitable ending. For all the vast timescales we have already explored in Neptune's story, from its violent formation billions of years ago to the centuries-long journey of light and radio signals still traveling between it and Earth, there remains one final chapter to consider, a chapter that unfolds not in the past, but far ahead in the distant future, long after any of us, and likely long after humanity itself in its current form, will remain to witness it. To understand Neptune's eventual fate, we must first look toward the star at the center of our solar system, the very source of energy that, however faintly, still reaches this distant blue world. Our sun, like all stars, exists in a delicate, ongoing balance, its immense gravity constantly working to collapse it inward, held in check by the outward pressure generated through nuclear fusion occurring deep within its core, where hydrogen atoms are continuously fused together into helium, releasing the tremendous energy that powers sunlight itself. This balance, though remarkably stable across billions of years, will not last forever. Currently, our sun is roughly halfway through what astronomers call its main sequence lifetime, the long, stable period during which it steadily fuses hydrogen into helium within its core. Scientists estimate this stable period will continue for approximately another 5 billion years, a timescale so vast that it dwarfs even the multi-billion-year history of our solar system that we have already explored throughout Neptune's story. Eventually, however, the hydrogen fuel within the sun's core will become depleted, triggering a dramatic series of changes that will transform our sun, and with it, the entire character of our solar system. As hydrogen fusion within the core diminishes, the sun will begin fusing hydrogen in a shell surrounding its core instead, causing the outer layers of the star to expand dramatically outward. Over time, this process will transform our sun into what astronomers call a red giant, a vastly swollen, cooler star potentially expanding outward far enough to engulf Mercury, Venus, and quite possibly Earth itself, entirely reshaping the inner solar system in the process. This dramatic transformation, however, unfolds on a timescale so gradual, stretched across hundreds of millions of years, that it bears little resemblance to any sudden, catastrophic event, occurring instead as a slow, steady expansion visible only across geological and astronomical timescales. For Neptune, positioned so far from the Sun at the very outer edge of the solar system, this red giant expansion poses no direct, immediate threat of engulfment in the same way it does for the inner planets. Neptune's vast distance offers it a degree of protection simply unavailable to worlds closer to the Sun. Yet the Sun's transformation into a red giant will still profoundly affect Neptune, even from such a distance, in ways both dramatic and, in some ways, quietly beautiful to consider. As the Sun expands into a red giant, it will also become significantly more luminous, radiating vastly more total energy than it does today, despite its cooler surface temperature, simply due to its enormously increased size. This means that Neptune, despite remaining at roughly the same orbital distance from the Sun, will experience a dramatic increase in the sunlight and warmth it receives, potentially raising temperatures across the outer solar system considerably compared to the frigid conditions Neptune experiences today. Some scientists speculate that during this period, the outer solar system, including Neptune and its icy neighbors within the Kuiper Belt, may experience a temporary, cosmically brief era of relative warmth, unlike anything these distant worlds have known since their formation billions of years earlier. This increased warmth would likely have dramatic effects on Neptune's icy moon Triton and on the countless icy bodies scattered throughout the surrounding Kuiper Belt. Materials that have remained frozen solid for billions of years, including surface ices of nitrogen, methane, and water, might begin to sublimate and evaporate under this new, more intense stellar radiation, potentially creating temporary but significant atmospheric changes throughout the outer solar system during this transitional period in the Sun's evolution. Following its red giant phase, our Sun will undergo yet another dramatic transformation, eventually shedding its outer layers entirely in a slow, gradual process, leaving behind a small, extraordinarily dense remnant known as a white dwarf, essentially the exposed, cooling core of the once massive star. This white dwarf will contain most of the Sun's original mass compressed into a volume roughly the size of Earth, and will continue slowly radiating away its remaining heat over an immense span of time, gradually cooling and dimming across trillions of years, far longer than the current age of the universe itself. Throughout this extraordinary transformation, Neptune's own orbital position will likely undergo subtle but meaningful changes as well. As the Sun sheds a significant portion of its mass during the later stages of its evolution, its overall gravitational pull will weaken correspondingly, causing the orbits of the surviving outer planets, potentially including Neptune, to gradually expand outward in response to this reduced gravitational influence. Neptune, along with any remaining planetary companions still orbiting the newly formed white dwarf, would likely settle into a new, more distant orbital configuration, continuing its ancient, patient journey around what remains of our once brilliant Sun, now reduced to a small, dim, slowly fading ember in the darkness. Whether Neptune's structure itself, its icy mantle, its rocky core, its faint rings and remaining moons, would survive this immense transformation relatively intact remains a subject of ongoing scientific modeling and speculation. Given Neptune's substantial size and its considerable distance from the most dramatic aspects of the Sun's transformation, many scientists believe the planet itself would likely persist in some recognizable form long after the more dramatic changes affecting the inner solar system have concluded, continuing its slow, silent orbit around the dim, cooling remnant of the star that once gave birth to it, billions of years into a future none of us will ever witness directly. In this sense, Neptune's story does not end so much as it simply continues, stretching forward into a future timescale, nearly as vast and difficult to comprehend as the deep past we explored at the very beginning of this journey, a quiet testament to just how enduring these great planetary bodies truly are, persisting across changes that will utterly transform the more delicate, fleeting conditions that currently make life possible here on Earth. And perhaps Neptune's greatest importance isn't what it is today. Throughout this journey, we have traveled across billions of kilometers, descended through crushing layers of exotic ice and superheated fluid, followed the strange backward path of a captured moon, and looked forward across billions of years into a future none of us will ever see. And now, at the close of this exploration, it is worth pausing to ask a simple but meaningful question. Why does Neptune matter at all to us here, on this small, warm world so impossibly far from its cold, blue shores? One answer lies in what Neptune teaches us about the fundamental processes that shape planets throughout the universe. As an ice giant, Neptune represents an entire category of world that, until relatively recently, remained poorly understood within planetary science. For much of the history of astronomy, our understanding of planets was built primarily around the worlds closest to us, the small, rocky planets of the inner solar system, and the enormous gas giants Jupiter and Saturn. Neptune, along with Uranus, revealed an entirely different planetary archetype, one built predominantly from icy compounds rather than rock or hydrogen gas, with its own distinct internal structure, atmospheric behavior, and formation history. This distinction has taken on unexpected significance in recent decades, as astronomers have discovered thousands of planets orbiting distant stars throughout our galaxy. Remarkably, among these newly discovered exoplanets, worlds similar in size to Neptune and Uranus appear to be strikingly common, perhaps even more common than either the small rocky planets or the massive gas giants that once dominated our understanding of planetary systems. In this sense, Neptune is not simply a distant curiosity at the edge of our own solar system. It may represent one of the most typical kinds of planet found throughout the entire galaxy, making our understanding of Neptune directly relevant to interpreting countless other worlds we will likely never visit directly, but continue to study from afar through careful telescopic observation. Every detail we have carefully pieced together about Neptune, its layered internal structure, its extraordinary winds, its unusual magnetic field, its diamond rain hypothesis, and its dynamic, ever-changing storm systems, provides scientists with essential reference points for interpreting the countless ice giant exoplanets discovered orbiting other stars. When astronomers detect a distant world of similar size and inferred composition, they naturally turn to what we have learned about Neptune to help make sense of what they are observing, using our own nearby ice giant as a kind of nearby, familiar benchmark for understanding worlds impossibly far beyond our own solar system. Beyond its scientific significance, Neptune also offers something more difficult to quantify, yet no less meaningful. It stands as a powerful reminder of the sheer scale and diversity of our own solar system, a place we sometimes imagine we fully understand, having grown up with images of neatly ordered planets circling a familiar sun. Neptune quietly resists this comfortable simplicity. It is a world of supersonic winds and vanishing storms, of a captured moon slowly spiraling toward its own eventual destruction, of a hidden ocean that may rain diamonds into crushing darkness, and of a magnetic field so strangely tilted that it defies easy explanation. Even after nearly 2 centuries of study, Neptune continues to surprise us, a humbling reminder that our own cosmic neighborhood still holds mysteries we have only begun to understand. There is also something quietly moving about how Neptune was first discovered, not through direct observation, but through patient mathematics and careful reasoning, astronomers calculating the presence of an unseen world purely from the subtle gravitational influence it exerted on its neighbor. This achievement reflects something deeply valuable about human curiosity itself, our persistent willingness to search for answers even when the evidence available to us is faint, indirect, and difficult to interpret. Neptune's discovery reminds us that some of our most remarkable achievements come not from what we can immediately see, but from what we are willing to carefully imagine, calculate, and eventually confirm through patient, sustained effort. As we consider everything we have learned throughout this journey, it is worth taking a moment to quietly gather Neptune's most extraordinary characteristics together, one final time. Here is a planet whose winds move faster than anything else recorded in the solar system, whose storms rise and vanish within a matter of years rather than centuries, whose largest moon defies the natural order of orbital motion, and whose hidden interior may forge diamonds within an ocean of superheated, electrically charged fluid. It is a planet discovered through mathematics before it was ever confirmed by sight, visited only once by a single spacecraft passing swiftly through its system over 3 decades ago, and yet a planet that continues to shape our broader understanding of planets throughout the galaxy, even from such an extraordinary distance. Perhaps what makes Neptune truly remarkable in the end is not any single discovery or measurement, but the way this distant, cold, quietly turbulent world continues to hold our attention despite offering so little of itself to direct observation. We have seen it closely only once. We understand its deepest interior only through careful inference and laboratory experiment. We watch its storms form and vanish across years we can barely track from such an enormous distance. And yet, despite all of this uncertainty, Neptune remains one of the most captivating worlds in our entire solar system, a planet that rewards patience, careful observation, and sustained scientific curiosity with genuine, meaningful insight into the broader nature of planets throughout our galaxy. Far beyond the warmth of the sun, Neptune continues its silent journey through the darkness, its storms still raging, its mysteries still waiting, and its distant blue glow reminding us that even at the edge of our solar system, there are worlds capable of inspiring endless curiosity. In the quiet, patient rhythm of its 165-year orbit, Neptune moves steadily onward through the darkness, largely unseen, mostly unvisited, and yet endlessly worthy of our attention, our wonder, and our continued search for understanding, however far that search may need to travel.